So maybe we wanted to kind of go a bit deeper into the reference documentation, what it is, what it contains, what are the goals of this document. So today we are 3 editors of the ZKProof reference document. Luis Brandao, who's here and is going to give the presentation with me. Eran Tromer, who's a professor at Tel Aviv University at Columbia and an advisor at QEDIT, actually, and myself. So basically, we're going to kind of give an introduction and a few aspects of what the second version or the 0.2 version of the document has, and then go through some recommendations. And we're going to have a small discussion after, because we're going to take advantage of the fact that another person canceled for today's morning session to discuss a little more there. So we're going to aim to inform about the community reference, and we want to really to motivate collaboration. As Yao was really emphasizing, we do want this to be a community effort. We want to make sure that you have the kind of incentives to contribute, and we want to hear your thoughts, right? So what's the goal of the ZKProof community reference, right? It has a lot of kind of goals and things we want to achieve with it. One of them, or 3 of them basically, are kind of to help onboard newcomers to the community. So someone that doesn't have no idea about zero-knowledge proofs, we want them to be able to reach to a specific section in the reference document that explains things maybe at a high level and kind of points them in the right direction as to what are the next steps for them to get more involved or to use this technology. We want to make sure that practitioners have a place to look for recommendations and best practices. Of course, so this specific text is actually going deeper into all of these purposes and goals and so on. And actually, it was a contribution by NIST to the second version. So I'm not going to read through it, but I do suggest you go to check it out. So we really put the effort to get the documents rolling from the first workshop, as we mentioned earlier. And we had several chairs that were basically in charge of different tracks. So we had the security track, the implementation track, and the applications track. I see people nodding because they were there. Many contributors. I mean, everybody there was a contributor, right? So everybody had a little bit of writing, some contribution that they did. And this was like really, I was personally amazed by how people actually got together and really co-created this document. And these were really the first steps for reference documentation, right? So the security track, what does it contain essentially? So we have there what are the basic kind of theoretical aspects of zero-knowledge proofs. So you have definitions. You see what are the different syntaxes and semantics for defining zero-knowledge proofs. We talk about the security assumptions. What are those that exist today? So from knowledge of exponent assumptions, going to Fiat Shamir, and discussing like all kinds of variants in between. We're talking about the different syntax and frameworks for building zero-knowledge proofs. So there's this kind of new way of thinking about zero-knowledge proofs that sort of derived from the first workshop that divides into 2 components a zero-knowledge proof scheme. On the one hand, you have kind of the information theoretic compiler, and the other one you have the cryptographic compiler. So this allows for a very neat modular way to build zero-knowledge proofs. And of course, there are several families that we discussed there. And then there is also some nuances for understanding ZKPs that Luis is gonna actually address in a little bit. In terms of the implementation track, so wait, maybe let me ask you, was there anyone here that was into the security track? Okay, that's what I thought actually. That's just to see how like this event is a bit more oriented to like practicing and so on than like really intense theory, but that's good. We need a little bit of everything. Who was here in the implementation track? There, Costas, yes, okay, good. So what we have here in this implementation track is more around literally implementing zero-knowledge proofs, right? So what are all the components that come here? So some of the things are like, what are the models that we are thinking of? So we have this idea of like front ends versus back ends, right? So in order to have a zero-knowledge proof, you need to first write the constraint system. So what language are you going to use? How are you going to define the gadgets that you're going to actually write to build these circuits, right? So actually, I'm talking in the language of R1CS based systems, right? This was kind of the first orientation, just because it's broad enough that this was the scope. But we are also aiming to further this to other systems, basically. We have, as here it was mentioned, interoperability. So there are several types of interoperability. You could think of interoperability between front ends and back ends. You could think interoperability between different implementations of the same scheme, from prover to verifier. You could think of, right, and there are several more. It's important to understand what are the caveats that come with this, and what are the best ways to overcome these kind of interoperabilities, so to actually have interoperable systems, which, by the way, includes kind of APIs and formats, right? There is discussion around how to do benchmarking properly, and what are some suggestions of how to do benchmarking. So, for example, one scheme, right, because we know that a lot of the schemes in the space, or most of the schemes, have completely different trade-offs. So you can go from having a trusted setup to not having a trusted setup, to a security assumption that is non-falsifiable or is falsifiable, to a prover time, verification time, prover size, proof size, RAM, memory, right? I mean, you have all kinds of trade-offs, and there is no one scheme that is appropriate. So for different use cases, you may want to use different proof systems. And the idea of benchmarking is around that. So to make sure that on the one hand, you give a proper kind of apples to apples comparison, but on the other, you're going to really result the benefits of using a specific scheme. Then we have also a discussion around SRS generation, given that it's actually kind of very, very prevalent in the most efficient schemes today, and how to securely produce MPCs for those. I think basically most of the MPCs today are using those recommendations, implicitly or explicitly, but it's pretty nice. And then there is also kind of a section around discussing what it means to have correctness and trust on an implementation. So this is a very important topic, I guess, especially around developers, because there is not always an assurance that the code that you're running is doing what you want it to do, and so on. And what we tried to do in the second workshop to address this point was actually to have a discussion around formal verification. So I don't know if anyone here is familiar with formal verification. Can I see some hands if so? Okay, that's actually pretty nice. So I definitely recommend and suggest you all come to the next workshop, which hopefully will have a bit more of this. And so the last, So the last document that we discussed was the applications track. So maybe I'll ask who was in the applications track. That's me. Okay. So here, the goal of the applications track was basically to sort of get more to the practitioners, to those that are trying to build the use cases, right? So what does it mean to build a use case for a zero-knowledge proof? So on the one hand, you have the kind of business level description, which then needs to kind of be mapped into like a protocol, right? So you can think of Sapling as such a protocol that has some functionality, which kind of maps it back to the business level. And then this protocol is actually going to have several different primitives. So you're going to have commitments, and you're going to have signatures, and you're going to have encryption, and you're going to have a lot more stuff to deal with, and hash functions and so on. And how does this kind of protocol really map within the security and privacy requirements to what are the proving statements, right? Like the predicates that are called, like really the constraint system that you're going to use to prove in zero knowledge. So we try to have a kind of overview of all of this, and what we do is we give a set of gadgets that. So these are not actual implementations. This was just in written. So we welcome anybody who wants to kind of contribute an actual open source set of gadgets, or at least one or something. We have this library of gadgets that we described. We have some exploration around use cases. So we discussed identity. We discussed asset transfers around the context of blockchain. And we had this regulation compliance. That was actually a really fun use case that we personally developed at QEDIT, but that was really kind of showcasing the potential, so around aviation compliance. And what we do is we have like these baby protocols as description. So we didn't go full-fledged to cover all the functionality in a secure way, because that would have been like really hard work, and it couldn't be done in 2 days. Yeah, exactly. It takes like maybe a year and a half to do one protocol.
2 years.
Yeah, 2 years, exactly. So it was hard work, but at least we wanted to showcase the power and how it should be done, or at least approached. And then we also go into a little bit of detail into what are the predicates that correspond to those protocols. So I encourage everybody to go and check it out. So maybe before I jump to the next slide, are there any questions around this? Okay, great. So what's the current state, right? So for the current state, basically, as I mentioned earlier, NIST started helping us. So specifically the Privacy Enhancing Crypto group at NIST, which is composed of Luis, Angela Robinson, and René Peralta. And so they came to the workshop and they actually contributed to the discussions. And before the workshop, really, they kind of transported all of the 3 documents into a LaTeX document that is now the reference document. And so we had many sessions again with focus to add content. So people were taking notes of the discussions. And we defined an editorial process. As I mentioned, there's 3 editors today. So that people could contribute. There would be integrations of those contributions into the reference document. And then we are now in the process of having a call for comments very soon. So I encourage everybody to look at these, to give comments and feedback, to be part of the contributions, because really I think everybody here has something to contribute. And so for the first round, which actually finished probably 2 weeks ago or something, I think it was 10th of October, we had about 15 total contributions. So that means that 15 kind of new paragraphs or sections or editing is taking place on the reference document, which is a pretty good rate to be the first one. And you can find the reference document and all of the issues. So the whole editorial process is around a GitHub repository. That's the link. So ZKP standard / ZK reference. You will also find here the 4 standard proposals, but there is no editing happening right now on the proposals. But you can see all the issues correspond to the reference document. So feel free to check those out. And now on to the second version. So I'm going to let Luis talk about what we've been doing.
My name is Luis. I'm with NIST. The reason to be here today is that NIST is interested in privacy enhancing cryptography. That meaning cryptography that has the potential to enable privacy applications. ZKProof approached us for some feedback before the second workshop. We found that there is great value in developing reference material, and that's basically our approach to this area. It's the idea of developing reference material, even though we are not committed to necessarily endorsing a standard right away. Okay, so here's a snapshot of the first page. So we're currently on version 0.1.x, which means we're currently integrating contributions. Hopefully in a few weeks we'll have the version 0.2 out. Feel free to contact us at editors@zkproof.org. So what I thought about doing here today, I don't want to go to low-level details of what we're doing, but I want to touch one aspect that I think is quite interesting. It was actually mentioned in the opening of this conference, which is the challenging of explaining zero-knowledge proofs to people who have never heard about it. But as we reflect a little bit about it, that's a challenge it's a challenge to explain to people who've never heard about it. It's also sometimes a challenge even to explain to ourselves, as we find ourselves explaining, are we really giving a reasonable explanation? So I want to touch on a few aspects that for which we've gave some feedback for this new version, which are essentially aspects at high level of explanation of what the zero-knowledge proof is, and which are related with making the reference document more accessible to a wide variety of people. And in particular, I think that one challenge is how do we differentiate between the 20-second explanation of what a zero-knowledge proof is, where somebody listens, okay, sure, you can prove you're an adult without revealing the birth date, and then the person never again thinks about it, versus making that explanation and then actually giving the opportunity to the person, wait a minute, how can you actually start doing that. And I think sometimes we don't do a very good job in actually giving that little extra step. I'll talk a little bit about it. So I'm going to cover 3 topics here, which is the first one is actually how do we give examples of zero-knowledge proofs, and then I'll talk about 2 slightly more technical, but I'll keep it high level aspects, transferability versus deniability, and also proofs of knowledge versus proofs of membership. Okay, so here's a question where I put some redundancy on purpose. At what level do we explain zero-knowledge proofs when we are explaining zero-knowledge proofs at a high level? And maybe as a little bit of motivation, let me put this question to the audience. Here are maybe 4 types of things where I could ask, can we prove this in zero knowledge? Can I prove in zero knowledge that I'm an adult? Can I prove in zero knowledge that my license plate starts with the letter A? Can I prove in zero knowledge that my favorite color is within this set, blue, red, or green? And can I prove in zero knowledge that I know a chess solution to this 8 queens puzzle? It's basically a case where you can put 8 queens in the chessboard and none of them is in check to the other. And let me just put the question to the audience. Is there any of these cases where you would say this doesn't fit very well as zero knowledge proof?
I would say no, yes, because the first 3 don't have enough information about what you're actually proving. They're proving something in the real world, but there's no connection to a formal statement.
Okay, I think that's a very good point, and that's one of the main points I want to do. There's kind of something missing, some support, but still a lot of times we talk about proving that we are an adult. So maybe if we put in what's missing, we can prove it, right? So if we're allowed to put what's missing, can we do all of this, or would there be still any of this that maybe you think it's kind of difficult? Okay, so just some nuances about these cases. So for example, if somebody says that I want to prove that I'm an adult, even if we don't have the supporting statement, at least, okay, we're pretty sure that this person is going to have a birth date. We might not have the supporting statement for it. The problem is, how do we confirm that it's correct, right? Now, my car license plate starts with an A. Well, do you even know that I have a car to start with? So we do have to have that supporting statement. The favorite color, indeed, maybe we can lie about it, and no one will ever know. And indeed, the first case is actually well defined on its own. It doesn't need anything else, I mean, except knowing the chess rules. So, and indeed, the reason to point out these cases here is to point out that indeed there is something missing in some of these use cases. And for that person that might be interested, who's never heard about zero knowledge proof, but maybe it's a technical person, we tell it the first time, oh, this allows you to prove stuff without revealing the confidential data. If this person actually has the intention, okay, let me actually try to figure out how it happens, this is not sufficient for that. And so this is one example of something that we look at the reference document, and for some of the use cases, we feel actually we're not giving all the information. It's good to keep it at a high level for people to understand it, but we also want to tailor this to people who actually want to understand the intuition. So indeed, the statement in this case may be insufficient to allow an actively interested listener to build more intuition. So as an example of something that we've did in the reference document as a proposal, so we picked some of the use cases that were immediately on section 1.1.1, like prove adulthood without revealing the birth date, prove solvency without showing portfolio composition. And there was a corresponding table there. And for example, in this case, we proposed adding something that would be the supporting statement. And so now for the person who's really interested in understanding how something can even start to happen, then you can say, well, you're going to prove that you're an adult without revealing your birth date based on the fact that maybe you have a smart card with a chip that inside of it has a certificate signed by the certification authority, and then maybe things can start making more sense. Not to say that the first case is not good enough. It is good at a certain level, but then we have a second, still high level way of explaining. By the way, the point of emphasizing some of these points here is, I guess this would be one of the conclusions, but I'm mentioning it now, is that one of the things that we would like to ask from the audience is that one of the best contributions you can give to the reference document is read the reference document and really state what are the things that are not clear to you. What are the things that are not covered by this reference document in the way that you see the world of zero knowledge proofs. Okay, second topic, proofs of knowledge versus proofs of membership. This was also a topic that we found that was not quite covered. And it's another case where if we start looking at the details, at some point, things don't match well. So often we say, at a very high level, zero-knowledge proof proves that a statement is truthful and reveals nothing else. Well, but what is this statement? Are we proving something of the sort, what we call a statement of membership? For example, X, our instance, let's say it's an RSA number. It's supposed to be an RSA modulus. It's supposed to be a product of two primes. So we can ask the question, is this X a number that satisfies this property? So does it belong, what we usually call technically, the language, let's say, of RSA numbers? In other cases, what we're actually making is a statement of knowledge. Let's say maybe you know g to the x, g to the y equals x, our instance, and you're proving that you know this value y, the exponent, that once you exponentiate the basis, you get this value. Now, sometimes these cases are interchangeable. You can swap between one and another, but not all of the times. And the problem, let's say, that we had at a first instance of the reference document is that the terminology was tailored to proofs of membership, but in fact, in a lot of cases, we're dealing with proofs of knowledge, and then in some points, things don't match well. So just to match some examples, for example, knowledge of discrete log, as I was mentioning, so x equals g to the w, where w is the witness. In some groups, basically, as you cover through all the possible witnesses, you have the full set of numbers between 1 and, let's say, p minus 1. So knowing that x is already an exponent, it's already g to the w, it's trivial. You just look at the number and you say it's in the language. So there's nothing to prove in terms of membership. The challenge is proving that you actually know the pre-image of some operation. Now, just to give a classical example, even though it might be a little technical, I'm not sure who might have heard of this, but for example, the set of pairs of graphs that are not isomorphic between themselves, basically meaning you can't permute the nodes of one to get to the other node. This is a traditional use case in cryptography because it's a case. This is actually a pretty hard problem. It's not known to be an NP. You don't actually have a witness, but you can actually do a zero-knowledge proof of it. So this is a particular case. I'll leave the details out of the conversation, but this is a particular case where you have a proof of membership if you actually are powerful enough to solve the problem to a verifier that is not able to solve the problem, but there's no witness to start with. And then we have cases which I think are more the usual for this audience in some of the presentations we've heard. You want to prove knowledge of a hash pre-image. Just as an I guess it's kind of maybe a theoretical interesting example. It's kind of the dual of this one. Also actually proving that X is actually, I actually made a mistake here, that actually X is a hash might actually be a difficult problem because not all hashes map away all the counter domain.
So there's another nuance here, which is what we mean by I know. So take, for example, a malleable proof system like Groth16. You can take an existing proof, malleate it, get a different proof, but you don't necessarily know the witness. The original proof will be the witness.
So sometimes you're proving that you know a proof.
Right.
So why mentioning this and why might this be important? Because the security properties are different. So and in one case, typically in proofs of membership, you'll have soundness as the property that you want for a prover. Cannot prove something if the statement is incorrect, if this instance is not in the language, versus extractability, which is what we want typically in zero-knowledge proof of knowledge. So this, for example, this is a particular case that actually still needs a little bit being worked out in the reference document. Okay, final example in this series. So transferability versus deniability. Go ahead, Jenna.
Is there a mention somewhere in the documents about the fact that zero-knowledge proof is a little bit a misnomer because most people or the statement that you're proving usually transfers lots of information or very important information about the underlying data, and just stopping and thinking about is the information that is being proven a big deal or not, it should be part of people's approach to zero-knowledge It's a bit about the talk that Costas made yesterday on differential privacy. Sometimes with all the stuff that you've proven, you know so much that you can go back and retrieve lots of things about the original.
I guess that starts to connect a little bit with differential privacy, for example. The current reference document does not mention that. That's the typical problem, let's say, we have in SMPC as well. You can prove that you can do a good SMPC where you just learn whatever you computed, and whatever you can extract from that. Now, is that a safe thing to learn or not?
There's a lot of cases where people hear about zero knowledge and they think, oh, great, that's my solution.
Zero.
But actually, the property that you're proving is covered under GDPR or is private. You can't really go and prove it.
Yes, and maybe related to that, this next topic, which is transferability versus deniability. So, actually, in the traditional definitions of zero knowledge proof, the initial ones, zero knowledge is always something that you cannot transfer. That meaning that if somebody proves to me something in zero knowledge, I don't even gain the ability to prove to another person that I interacted with the legitimate prover. But in a lot of the use cases that we heard yesterday, we're actually dealing with cases of transferable proofs. Proof that we actually want to put in the blockchain, and then anybody can check that is true. Now, each of these properties can be considered a feature, so transferability or its opposite, deniability. So deniability would be, I got convinced of some proof, but now if I try to say to somebody that, oh, this person just proved this to me, the person can say, no, I didn't do that. So that would be deniability. Or sometimes these things can appear as a bug. So I would claim that this is an important thing to bear in mind for people who implement these kinds of systems. So as I mentioned, traditional zero knowledge proofs are deniable. Certain applications can benefit from transferable proofs or publicly verifiable properties. Let me just go through a few examples, kind of to a little bit test the intuition. So in a non-interactive setting, so where the proof is just going to be sending a message, can you have a deniable zero knowledge proof of knowledge of a witness, where you just send a message, and this single message, okay, maybe we have some kind of setup, but now I just send a single message, and I want this message to be sufficient to convince the verifier I'm sending it to. Given that this is a single message, there's no kind of challenges with interaction, can we somehow make this deniable? Or is this for sure transferable?
Do you allow some sort of previous implicit communication, like people agree on a common reference string?
Yes, for example. You can have a PKI, for example.
I guess it depends exactly how you define deniable.
True.
It's possible to set something up with a VDF.
A verifiable delay function? How would you do it?
Well, you'd have to guarantee that by the end of the VDF, you release your commitment so that either the commitment or your original information you're proving could be passed in as the parameter.
So by the end of this time slot, the person learns the private information?
Or no, that can pass in the result of the VDF to say that it could have been either the private information
okay.
or...
Okay, pretty good. Yeah, that's the kind of example that I would have, slightly different. So if you actually have a PKI, a public key infrastructure, then what you can do is instead of proving that you know W, you can prove this disjunction, I know W or I know your private key, which means that this proof the verifier itself could have produced because the verifier knows its own private key, right? And so in this kind of proof, now the verifier cannot transfer this to another person because they'll say, well, you might have generated this on your own because you know your own private key. Okay, so interactive setting, can it be transferable? It's kind of the opposite. So we have an interactive proof.
Yes, because you can consider anything with fiat shamir to be a kind of interactive proof.
Right.
I mean, a non-interactive proof is a special case of an interactive proof. So
Yes, and even if it's interactive, indeed the verifier can do exactly what the fiat shamir operation would do. So it just computes the challenge as a hash. So this one is kind of the classical one. Just kind of it's a kind of a funny case. It might have some applications. So you can actually have received a transferable proof, and now, so I don't know the witness. I don't know that whatever is the secret information that allowed me to be convinced of a certain proof. But now that I got this transferable proof, I can actually give to others in a non-transferable way a proof that I have a transferable proof. And anyway, I just think it's kind of funny. Maybe it has some application.
Just having a question here. Would it be needed in order for the interactive setting to not be transferable? Because usually that's the kind of default that you're talking about, unless you're talking about like designated verifiability.
Sorry,
what's also sort of transferable?
What is the basic setting you're saying?
So I'm asking whether, in order to make an interactive proof non-transferable, you would just need to kind of set the implementation so that the randomness is specific to the verifier.
Yes, there's also some techniques where you can basically do coin flipping between the two parties to ensure that the verifier cannot compute a hash.
On that interaction.
Right.
On the actual.
Yes. Other cases would be where you have let's say a reference string that is actually private to the interaction as well.
Because in this regard, there is also the interesting case of public designated verifiability. Like there are schemes that basically encrypt the proof to a verifier, right?
Right.
You can just decrypt the validity of the proof with their own key, but you can transfer the key.
Right. So is it just encrypted so that an eavesdropper doesn't see it, or to actually prevent that the verifier can actually prove to another? Yeah. Okay. So actually, one example, kind of, I don't know exactly how much this might be applicable, but imagine an auditor obtains a transferable zero-knowledge proof transcript. That might be part of a protocol. But now the auditor actually does not want to reveal this information that it learned from the clients. But maybe for some ongoing investigation, it's able to actually give a deniable proof of what it learned. And now...
what's the motivation for deniability like, in day-to-day life?
Well, let's actually pick the use case that you're saying, that when you join too much data, you can actually then kind of make some kind of profiling. So let's say today I'm proving that I'm over 18. Tomorrow I'm proving that I'm below 21. Now you combine this data, you already have a little range of things, right? If I give, and now you can publicize this to the world and people will be convinced of this. If I only give you deniable proofs, then to the world, whatever you publish cannot be actually linked as something that I've proven.
I see. So it's a way to avoid an exploration of the original data.
Could be. I would say that this is indeed one bit of information, this transferability. It's not one bit of the secret data, but it's one bit that an interaction has occurred. And with deniability, you actually remove that bit. So it's kind of truly zero something, zero knowledge.
It's zero knowledge in the meta state.
Yeah. And just another use case. So a case of the problem that we often have when we compose protocols with the environment.
So why not do it all the time? Like, what's the reason not to do deniability?
Well, because, for example, in the case of blockchains, I guess what you actually want is you actually want transferability. You want anybody to go there and check that the proof was correct. So somehow you're differentiating between the bit of transferability versus the actual bits of the secret data. So you want the world to know and to be convinced that a legitimate prover actually proved that assertion, but without revealing any bits of the actual data. But still one bit was leaked, the bit of information that a legitimate proof has occurred. Daniel, how are you? Time, please?
15 minutes.
Good, okay. Just this final use case of composability with the environment. So assume now that you actually have a deniable proof, interactive deniable proof. But now for some reason you're implementing your protocol in a system where all communication messages are authenticated and timestamped. So by default, you didn't think about that, and just as a matter of security, each time you send a message, an email, you actually sign it. So now actually, whoever is the receiver, even though the protocol at a higher level was deniable, now the receiver can show, no, look, this was really the prover who sent me this message. So sometimes you have this kind of composability issues, and this is where usually these nuances about proofs of knowledge versus proofs of membership, arguments versus proofs, that's where they may be important. And I think for this community, at least for the people who really want to implement things and make sure that we're building trust, that's something we mentioned very vividly yesterday, and we don't want to have security problems, some of these subtleties are actually important to be taken in consideration by, at least by the more technical people involved in this.
Another issue, for example, is sometimes you want to tie the proof to a particular protocol context.
Mhm.
So in Zero Cash, for example, you want the proofs that are inside a transaction to be tied to the transaction, so you can't change any of the metadata
Right.
while still reusing
Some kind of
reusing the proof.
non-malleability. Mhm. So these were the examples that I wanted to give about the some of the feedback that we gave to the reference document. Again, to kind of illustrate that I think it's quite important that the community reads the reference document and really tries to figure out, are the explanations clear? Are they covering the cases that need to be covered in your context at least? So please consider contributing with your feedback. Look up with a magnifying lens, and if you find anything that you think could be changed, either give the suggestion or even propose the text that you would like to have there. Okay, next step, this was actually a duplicated slide that's going to show up later. Some recommendations that appear in the reference document, just to exemplify a little bit of the content, and then also to actually introduce an idea that we would like, at least the NIST spec team would like to promote. So, okay, one example of something that was worked out a little more towards this new version 0.2. So, proposing, we're calling requirements. I mean, it's not like somebody is obligated to do this, but it's requirements to be within this context of interoperability and all that with respect to benchmarking. Then, so for example, with respect to computational security, then currently the new version 0.2 to come out soon will require that benchmarks are done, at least that one benchmark is done with computational security of 128 bits, and it also suggests that it be done with an extra parameter to basically allow comparisons. But
when you mean benchmark, you mean like a minimum?
Yes, minimum level. Yes, so kappa greater or equal than 128.
So, what do you do about the fact that sometimes it may be difficult to establish an exact security level? So, for example, you're using a pairing-based protocol, and we're not exactly sure what the best attack on the target group is. So, say using BLS 12381, it's a little bit controversial whether it's actually
Right.
128 bits or not.
Right. Well, I guess that's why often we say security level, and we just put it there. Like, do we really know if RSA 3072 bits is the 128 bits? I guess to a certain extent it has to be best effort. And then the community over time eventually says, this is actually really not in this level, so you should be using something else. This in particular would mean that we would achieve soundness and zero knowledge in the long term against long-term precomputations, against the adversarial computation during the protocol, and also against, at least in the case of zero knowledge, even against post-computation, where maybe something is encrypted, you need it to be encrypted in order to really be zero knowledge proofs. Now, I guess this is more or less trivial computational security, maybe something that I think usually passes a little more,
Another issue, this is presumably pre-quantum, all of these.
Yes, so currently the reference document also asks for, if you can do post-quantum, if it makes sense to do post-quantum, then probably sometimes the keys have to double the size. The case of statistical security, when we have interactive protocols, actually makes sense for lower levels of security. So this would be what we sometimes call the one-shot adversarial attack, where the adversary has a 1 in very large size chance of guessing, let's say, a password or something. And if it guesses that, then it can actually break the protocol. But these are not protocols like, okay, I'm going to do brute force and I'm going to eventually reach 2 to the 64 power of computation. No, this is a case where there's 2 to the 64 chances, and either I get it right in that single time or I don't get it right. So in these cases, actually it's okay for the statistical security parameter to be much more than 128. Typical cases, let's say for MPC, would be to use 40. Even in other cases, people use 30, for example, which basically means an error probability of 2 to the minus 30 or minus 40. One point, though, to notice is that if you have an interactive protocol where you say it's perfectly fine to have 40 bits of statistical security, but if then you want to make it non-interactive by applying Fiat-Shamir, then you actually have to increase the statistical security parameter, because now you are in a setting where the prover can actually pre-compute, okay, this doesn't work, I discard it. This doesn't work, I discard it. And it can actually try 2 to the 40 times until it gets one that it works. Okay, I was pressing the wrong button. Okay, just a little note, exceptions for lower security. Actually, some of these might be warranted. With the disclaimer, be very careful about it. So actually, in some interactive protocols, there are parts of the protocol where you just need short-term security. Let's say you're doing a coin flipping, you're doing a commitment, you just need this commitment to be hiding and binding until the point where the other person reveals something, because after this step, you're actually going to open the commitment. And so for that case, if it actually makes a big difference in terms of efficiency, then you can potentially have a lower security parameter. Again, being very careful about it. Another possible use case is, well, actually, if you're proving a predicate that itself is protected by a very low security, like I'm proving that I know a pre-image of this hash that ends with 30 zeros. Well, you pretty much need 2 to the 30 computation, power of computation to do that. So you can actually, in some of these cases, use a shorter proof level. Okay, some bench. I think I'm actually taking a really long time in this. How am I doing, Daniel?
Like 5-10 minutes.
Okay. Okay, so the reference document gives some suggestions about benchmarks. I'm actually going to skip this in the interest of getting to more interesting stuff. Basically, there's a lot of metrics to compare. There's potential use cases to exercise the methods on. But let me ask a question. What about the cases where efficiency is no longer a big deal? Maybe you want to do the case of Alice wants to prove that she's adult, and we have an easy setting, and out of the 10 best techniques, all of them do perfectly good, between 0.1 and 0.2 seconds. Do we need to do benchmarks? Do we need to do anything else? Well, what I want to propose is that something that would be very useful for this endeavor is that we build what I would call here a use case suite that could facilitate experimentation by new implementers. And what this would mean is that, forget about efficiency, let's just assume that efficiency is solved. How does a person who just heard about zero knowledge proofs, maybe it's a technical person, knows how to do programming and all of that, how is it actually going to build their application based on stuff that might be available somewhere? So the proposal basically, and this is something that we at least at NIST, we're thinking of doing this soon, and I think this overall can be a community effort later on, it would be nice that we could collect fully functional open source implementations of very concrete use cases, very simple ones. Doesn't need to be the use case that the company is highly invested in, because maybe the company wants to have that for themselves, but let's just pick very, very simple use cases for which we can have 5 or 6 examples, and then whoever wants to use these things can go to this repository and actually learn by example, as we often do when we're just doing some kind of programming. So NIST the Privacy Enhancing Cryptography, wants to propose such a suite. Maybe within 6 months we'll have something, maybe before that we'll have a draft, and we intend to include things like zero knowledge proof, secure multi-party computation, basically things within the full spectrum of PEC.